Well, hello, Internet. Good morning. Uh, it's pretty early in the morning here on a Saturday, and I'm pet sitting. But I'm really inspired to just code. Yeah, hey, look at this. I got a little bit of coffee. Yep, I got a little bit of coffee. It's decaf. Yep, but it's coffee and it tastes good. Okay, so you know, let's maybe go to the idea board here because, we almost got the file reading thing to work last time, but that was pretty hard, because we're trying to tokenize. That's one of the big goals is to tokenize. Okay. So if we go to the drawing board here, we're trying to, oh my goodness. Okay, can this go away? I just want to make a document. All right. So let's see here. To do. We are trying tokenize. We are trying to tokenize the oh yeah. So we were trying to tokenize the meditations text. I wonder if what was I thinking? I was just thinking something. I was wondering if I wonder if we make a word bank that our program can choose from and several sentence styles that it can use to build stories. Let's do that. Let's consult the Oracle here. You know what? How do I? This is literally. Come on, let me rename this. Okay. The Oracle. Okay, that's who this is, everybody. For all intents and purposes, this is the Oracle, and here we're gonna not default to the same chat every time. All right, Oracle, we want to ask you something. Okay. All right. So maybe we could say describe different sentence structures in English. All right, simple. Okay, single independent clause. Joined by a conjunction. Complex sentences. Okay, actually, so maybe for our Mad Lib, we can do a simple sentence. Simple sentences. Interesting. All right, I like this. This is a good chat. Okay, next thing. So that's good. All right, let's work on tokenizing. So we did some research. That was good. Some R&D. Well, let's work on this tokenize function. Oh my gosh! Well, look at all this gobbledygook. Okay, so we're gonna read it into memory to some kind of char array, but we were getting some weird things happening, right? Like we were getting some weird things happening, I think. All right, let's see here. Marcus Aurelius.c. So let's compile that. ./a.out. Okay. So we got at the same time he was kept from the extravagancies of his day. I wonder if that. Let's pull up the main text here. Meditations, Marcus.txt. Extravagancies. Excuse me. Okay. Where was it? From the fiercest boars. The Emperor Hadrian. Okay. Kept him from the extravagance. At the same time, he was kept from the. Yeah. Okay. So here's the thing, dude. Dorian, I think what's happening is it might just be over. Dorian's my friend. I don't know. Anyways, here's the thing. No, I'm just kidding. Dorian's my name. Okay. That's kind of why I called this Stojan Studios, because I was trying to be anonymous. But hey, I spilled the beans. My name's Dorian. Hello, internet. My name's Dorian. Good to meet you. It's not Stojan. Oh, dude, it's so funny. See, man, my guard's down. Okay. Oh, yeah, there we go. For some reason, it looks like I need a software update. It says one update available. Pulse Audio Sound Server. Okay. Okay, just do the thing. Okay, looks like it's doing it. Bear with me, everybody. Thank you. It's just that dot, that orange. I see red, and I'm like, oh, orange dot. All right, so it's reading each line, but it looks like it's overriding our buffer. Oh, hold on a second. When we realloc, okay, come back here. Describe realloc in C. Okay. The prototype. Give it a pointer. Previously allocated memory block can be a null pointer, in which case it's like malloc. Realloc returns a pointer to the newly allocated memory block, which may or may not. Okay, here's what we need to do, y'all. We need to actually learn how realloc works, okay? So we're going to go to main. We're going to copy out, comment out, ignore essentially our meditations code up here for a bit. And we are going to say char star I don't know, string price rate content equals realloc. Wait, hold on. Null. Let's kind of give it something first. And then we'll say content equals realloc content, and then size of, we'll just say size of char. We'll say, I think you dereference the pointer. So you say star content equals A, for example, and then we say content equals, actually, let's print f first, %s content. Okay, so what we're doing here is first we're creating a pointer. Okay, we're creating that's what this little star means. In C world, okay, which is C world like Shamu. Okay, in C world, like C and C++ and all that, you got this concept of pointers, all right? And pretty much whenever you see this little star, if it's not multiplication, okay, so like multiplication would be, I'm going to create a number variable here. Excuse me. Like an int, an integer, which is a certain size of number, okay, in memory. Int number equals 5 times 4, okay? This here is the math operator multiply in this context, but whenever you use it like next to a variable name, not next, well, it's kind of hard to describe. Wow, that's really hard to describe. Okay. Okay, whenever it's not being used in a way that the compiler would interpret it as multiplication. So like if you had number, 1, for example, and int number 2 equals 4, okay? And we say, we have these two numbers, and then let's say, okay, int result equals, number 1 time, number 1 time number 2. See, this is multiplication. Now, you know what? Let's do some things here. I really want to just drive this home right here because it's really important. Okay. So, print f, we can actually print these results. So print, percent is our escape character to insert runtime variables into our string. These are numbers, so D for decimal. %D times %D. And this is all a string. I'm not actually right. This is not code, This is not going to actually multiply here. All the math happens here, okay? Here, actually, we'll just write it out. Okay, that's easier, okay? Less confusing. All right. That times that is %D, okay? And then we're going to throw in number 1, number 2, result. There we go, okay? Okay. All right, now if we compile this, okay, so if we GCC Marcus, I believe, yeah, and then we do /a.out, Yeah, look at that. 5 times 4 is 20. So I just illustrated how the math works. Now, what can be kind of crazy. So this is where the cool computer science comes in, right? Have you ever heard of a RAM chip? Okay, RAM chip. Let's see here. Maybe I can upgrade my plan. How much is it to upgrade plan? I want to get Dolly. Oh, dude, that's expensive. 20 a month? What the heck? Heck no, dude. Okay, can you draw diagrams? First of all. Oh, ASCII art. Okay, great. Okay. Can you create an ASCII art for a RAM computer chip? How it works? Okay, so they're creating a RAM. Yeah. Okay, so all right, whatever. Okay, so circuit, computer motherboard. Give me a computer motherboard here. Images. Oh, here we go. This is it. This is what I wanted to see. Is this? No, I don't want copyright. Okay, just give me uncopywritten. Come on, give me like a real motherboard. Yeah, like that. Okay. Okay. Oh my goodness. Save the image. Save it to my downloads. Okay. Okay, so let's just look at this image for a second. All right. Well, what's even going on in here? Okay, this is really when it gets important because you got to connect the dots between what's in here, okay, in the file, the C file, and what goes on in the chips, okay, in the actual physical hardware, okay. All right, so what I was just talking about, that RAM chip, those sit in this big long slot here, okay, and that is a beautiful representation of how RAM works. Okay, it's like a list, a big stack. That's why it looks like a stack, right? The chip is not in the board yet. See how the slot is actually, the slot is empty. There's no chip in there. There's no card in the slot. However, if there was, it would be a list. Okay, so it's a list. You think of each of these lines as like a little portion of the whole memory that you have available. Okay, and then this is the brains of the operation, the CPU, the central processing unit. Okay, and this is so think about it like this. Okay, anytime we do something like multiply, okay, so multiply, yeah, that's better. Okay, no, that's not better. Okay, there, that's a lot better. Okay, so anytime we do something like multiply here, okay, that is when the CPU really takes over for a while. Okay, does a lot. Um, Whenever we say, boom, whenever we essentially reference a variable, okay, so we're accessing some memory, right? Because number one is just or number one and number two are just symbols, okay? They're just symbols. We created them as programmers. We created the symbols number one and number two, and we said, hey, these symbols can refer to data of this type here, okay? This type, all right, which is an integer, which the compiler does its best. Remember when we type in GCC? So the compiler, that's GCC, all right, or Clang or whatever you're using on your computer to compile this code into A.out, which is your binary ones and zeros for the circuit to read. Excuse me. So anyways, this is your data type, and that is a compiler construct, all right? That is a compiler construct. Okay, so we got those all kind of defined here. But anyway, so this kind of thing is what the CPU does. It says, oh, you're using the star symbol. That means I need to multiply. And the CPU has a logic, construct, a little hardwiring in it that lets it do multiplication, essentially. I mean, it definitely uses a lot of software to do that too. But at the end of the day, it's just literally wires, okay, in the freaking chip that are set up in such a way that when you input two kind of, or you give some inputs and then it multiplies them. It's essentially how it works. Now those wires are probably reused in a lot of different ways to support other operations too. But all I'm trying to get at is mathematics is done by the CPU. Okay, that is done. So multiplication is done here. Physically, it happens here. This is where the wires do it. Where do we get number 2 from and number 1 from? Where do we get these numbers from? Well, the CPU grabs them from here. Okay, these chips. That's how that works. Okay, so there's my crash course on the CPU, Central Processing Unit, and RAM, which, by the way, RAM stands for Random Access Memory. It's pretty fascinating stuff too, like the technology. I literally think, and definitely correct me on this in the comments, but I literally think that RAM just creates an infinite loop on itself with a wire, and when you pass it current, it just holds it in an infinite loop, and that's like a 1, in binary. It just holds the current in a loop, doesn't let it out. And then when it gets sent another circuit, it helps it to discharge that current so that it doesn't have current anymore. And that's a 0. And I think essentially that's how RAM chips maintain state on the motherboard, is holding current and releasing current, and then reading that current, to interpret it. It's so wild. Like when like I always think about this because I was born in like 1998. Okay, this stuff I think was being developed like when was a computer RAM chip invented? Like, whoa, 1967? Like, I'm just like, I'm just gonna take a quick coffee break here. Like, what? Like, in 1967? Okay, let's think about world events in 1967. What world events occurred in 1967? Okay. I want to know big ones. Oh, look at that. Wikipedia's got a whole article on 1967, okay? Look at that. Charlie Chaplin launched his last film, A Countess from Hong Kong. Charlie Chaplin was still putting out movies, man. Oh, dang. Vietnam War was still happening. I wonder if military had anything to do with computers. I bet it did. I bet it had a huge factor on computers, intelligence, something like that. I don't know. So maybe that's why, maybe some military stuff drove computer innovation. You know what I mean? I'm just like wondering where the researchers' money was at. So under IBM, filed a patent under IBM for a single transistor DRAM memory cell based on MOS technology. That's interesting. There's a patent on it. Okay. DRAM. That's cool. So this RAM chip had a capacity of 16 megabits, which I believe is 16 million bits. So I think at any given time, at any given moment in time, this chip could hold 16 million ones or zeros at one time. Okay, 16 million bits. That's kind of a lot of bits. Isn't it 16 million? But I mean, if you think about today, like you have, I think this was the standard RAM size of an iPhone. I don't know. DDR4X, Dynamics something RAM. Okay. Yeah, like 4 to 8 gigs. Or 4 to 6 gigabytes. And I think it goes from mega to giga. What is the giga unit? It's a billion. Yeah. So we're talking 4 to 6 billion. Freaking ones and zeros at one time. Okay. Now, I did say something earlier. I said something called Stack Overflow. Stack Overflow, I think in the last video or something. But essentially what that is using up all the RAM. You run out of those ones and zero slots. Okay. You literally, your program tries to set this bit and then set this bit and then set this bit and then this bit. And it does every single one all the way to the end. And then the overflow part is it says, okay, I want to set another bit. Oh, I'm out of memory. And then it goes bang, error, and the program terminates. Okay. Now, and I'm doing this for me because this took me a lot to wrap my head around, listen to a lot of things. And so this is the multiplication. It's somehow the compiler, just based on the orientation of these symbols and stuff, the compiler knows, okay, when you put a variable here and it's a number, or I guess if it's just a variable, and then you put a multiplication sign in between another variable, it's going to multiply. However, this is where things get funky, okay? Okay, so you know what? Like, let's do some pointer stuff. Okay, so let's say, we have the number 5 and 4, okay? We'll say we want to use them, okay? But we want to give them some kind of alias or something, or we just don't want to copy the data, okay? We'd rather copy what are known as pointers to the data, okay, references. So let's say, int star, so an integer pointer, we're going to call this pointer 1 is equal to, now I think to say the reference of this, like this number is like ampersand number 1. I think that's how it works. Okay. what are we doing here? Okay. This is where it gets funky. All right. So CPU comes through our code, right? It's like int number 1 equals 5. Okay. What does it do? It's got a symbol. Okay. Number 1 is somewhere in the chip, or in the motherboard, the whole thing, the chip. So the symbol number 1 is in there. And then what it does is it looks in RAM, okay, in the proper spot for an open slot, or an open section that it can put all the data for number 1, that symbol number 1. And it finds that spot. Let's say it's right here, kind of in the 2/3 mark of the chip, of the RAM chip, okay? And it says, okay, where is this? It says, where is this? It finds the exact number, essentially, that slot is. And it takes that number and it says, hey, you know what? In our little table of symbols, okay, or whatever, number 1 is going to be 8,000. RAM bit 8,000 is where it starts, okay? So anytime we use number 1, we're going to go to our symbol table or whatever and just grab 8,000 and then go to RAM. And then once we're at 8,000 in RAM, then we can grab all the data that it is, okay? So that's how that works. Now, the 8,000 that I was just talking about in that symbol table, that's known as a reference or a pointer. That is what that all means. It's what is the address in this RAM chip that I'm storing the actual data that we care about. So it's a very much overhead thing. That's what a pointer is. So the number 5 gets stored at 8,000 or whatever in the form of binary. Okay, so what is 5 in binary? I don't know. Let's freaking Google it. What is 5 in binary? Okay, this is 101. Okay, so you need 3 bits. So, maybe, but, we actually said, okay, hey, this number is going to be an integer, okay? So, this is where that size of operator comes in to play. So we're going to say size of an integer in bytes. Okay, so now we have bytes. So we have %d. All right. All right, size of an integer in bytes. And we're going to say size of int. Okay, so we want to know how much memory gets set aside when we say int. Okay, so now let's compile our code again. Oh, okay, so here's a compiler error. Size of does not return a plain integer, returns a long unsigned int. So we need %ld. Oh, nice. GCC is becoming a nice, good compiler. Okay, but all the cool people, all the cool kids are using like Rust these days. I want to use it at some point. I'm a little nervous. It seems scary, but I think I should just use it at some point. Mainly I'm using C because a lot of people, that's what their like professors are using and stuff. Like it's just a little bit more mature, I guess. However, Rust has been around for a bit now at this point. So we're going to compile it and we're going to run the executable. Oh, here, that's hard to read. Let's throw a new line at the end of each of these so that we get some easier to read text. Okay. Oopsies. Forgot to compile. So I saved my C file, but I ran the old executable. So that's why you always have to recompile your C file before you execute. Okay. So look at that. We got 4 bytes. Okay. So a byte is a standard of unit, a unit of measurement. Okay. How many bits are in a byte. Okay, 8. Boom. And what is a bit? A bit is a 1 or a 0 in a string of zeros and ones. So when we said the number 5, okay, the number 5, what is 5 in binary? Okay, is 101. Well, that's only 3 bits long. And I think so. When we said int, okay, how many bytes did it say? Bro, four bytes. So 4 times 8. That's 32 bits, 32 binary bits. Okay, 32. Okay, 32, huh? Wow, that's a big number. Okay. So what is the math? So here's what we got to do. Print f. So approximate largest integer. Okay, so this is kind of like the max number we can make here, 32 bits. Is %d. Okay, so here's what we're going to do. We're going to actually create a binary literal doing 0b. Okay, 0, the first one's kind of like the sign, like is it a negative or positive number? Let's do 31 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Okay. Look at that. That's the biggest number we can use. You know what I mean? That is, so when we say int in our code, we're saying, hey, computer chip. Oops. We're saying, hey, computer chip. Okay. I want you to set aside 32 of these little ones and zeros circuits, little slots. 32 of them, okay, out of the, what did we say? If it was 8 gigabytes, that would have been 8 billion bytes. Oh my gosh, what's 8 times 8? So 64 billion ones and zero slots. Out of the 64 billion ones and zero slots, okay? 64 billion. I want you to set aside 32 of them. That's what happens when you say int. Give me 32 of the 64 billion. So it's very hard to overflow that, right? Let's do it. Let's overflow it, okay? Let's literally do a Stack Overflow. Okay, I don't even know how to do that in. I just need to allocate. I need to keep allocating until I can't allocate anymore. So while true, this is a little hack here to just create an infinite loop. It's not a hack. It's just bad practice maybe. I don't know. So while true, okay, we are going to here, let's say char star character equals char star character equals malloc. How does malloc work again? Oh boy. Okay. How does malloc work again? Fibonacci. No. How does malloc? Describe malloc and see. Okay. Malloc. So, okay. Give it the size. It's that simple. Give us a size of. Oh, here's something simple. Okay. 1, 2, 3, 1, 2, 3. So we're saying give us 1,000,000. So malloc is kind of the even lower level way of saying just give us some memory, okay? Give us size of, I don't know, a chart, 1,000,000 characters, okay? Let's do integers because we just saw that. Okay, so we need 32 bits. If we get 1,000,000, that's 32 million. If we only have 8 gigs of RAM on this computer, to Stack Overflow, we're going to need to take that, what is it, 32 million, and we need to turn that into like a lot. We don't even need to use this while loop. We can just hard code it probably. Let's try it. So instead of 1 million, you know what? Let's go 1 byte at a time. Okay. Let's go 1 byte at a time. Okay. Let's just do malloc 1. Okay. Because I'm not actually sure if that will work. So while true, we're going to say character equals realloc. And then describe. I wish this was like a terminal where you could do repeat your history. Describe realloc C. What is the prototype? There it is. Give us the pointer and give us the new size, I think. New size. Okay, so we're going to say realloc, character, and pass it the new size. Okay, so we'll say, I think, no, we need this to be a massive number. What's the largest integer? What was the largest integer? 6. It's only like 2 billion. That's not that big of a number, okay? How big is a long? Okay, what is generally the general size of a long in C? 32 bits. However, it's typically at least it's about 2 billion. What is the okay? So how do I store? What do we need for bytes? Wait, 32 bits. We need to overflow our RAM. Okay, so how do we do that? We need like a lot of data. Okay, we need how do we do this? We need to say, well, that's how many bytes divided by 8. 8 times that, 16 billion bits. So it's not quite there. Just stick to bytes, all right? 2 million is the number. All right, let's see. Size of long is, what does it give it? How long? At least 32 bits. 4 bytes. Okay, 4 bytes. So that's 4 bytes. What is the biggest long in C? Okay, long is massive. I think we can do that. So let's do long size equals 1. Okay. Let's malloc with our size. Okay. Let's come down here and we're going to say realloc. We're going to say size times equals 2. We're just going to double it every time. Okay. Then we're going to say character size. Okay, let's try that and just see what happens. Okay, bear with me. The computer may crash. Okay. Do I see? Excuse me. Maybe I need to do while one or something. There we go. Come on, give me a Stack Overflow here. Computer's heating up. Anyways, I don't want to crash my computer. But I think, okay, it would probably crash something. Program the computer. This is a bug. You don't really want this to happen. Okay, you don't want to just keep allocating, and hogging up all the resources of the CPU or the RAM. Okay. Anyways, hey, thanks y'all. Figured I'm just trying out different things, with these videos. Sometimes I like to do tutorials. I mean, I was actually like a teaching assistant back in university for like 2 or 3 years, in computer science, in a computer science program. That's what I got my degree in. And I was also a private tutor. So I love that kind of stuff, like breaking down things into kind of how people want to hear or learn about or hear about. If it's visual, I like to do like visual talks. I like to use like whiteboards. I like to use real code examples. I mean, and I like to have fun with it too, because at the end of the day, it's fun and it can be useful. Like you can make a career out of it. It's just a very, very cool area to be in. And then I also like just doing projects, and having some coffee, and just having some fun, before work or whatever. But like I said, today's Saturday, so don't got much going on. So I just wanted to throw out another video. But I'll see y'all around. Thanks, Dorian, signing out. Yeah, thanks for checking out the video, and I hope to see y'all around. Please leave a comment. All right, take care.